Hello, welcome back. In the last videos, we talked about the addition principle and the multiplication principle. Today we're going to talk about a couple of principles that involve subtraction. Let's see why. Here's an example. A computer password can be made out of lowercase letters, uppercase letters, and digits. The numbers 0 through 9. Let's try to count the number of 8-digit passwords that have repeated characters. Let's think about how we would go about calculating this using the multiplication principle. In order to do that, we would need to determine which characters are repeated, where we're going to put them in the word, and then deal with the fact that there's some overcounting due to overlap in how we choose where the characters get placed. There's a simpler way to do this. Let's think about the structure of this set of passwords. We're trying to count 8-digit passwords that have repeated characters. So if we took the set of all passwords, some of them have repeated characters and some of them don't. So that means if we know how many total passwords there are and take away the passwords that have no repeating characters, we'd be left with the set of things that we want to count, the passwords with repeating characters. As an equation, we would say the number of passwords with repeating characters is equal to the number of total passwords minus the number of passwords with no repeating characters. So let's do the math. We're trying to figure out how many passwords have repeating characters, and happily, the number of total passwords and the number of passwords with no repeating characters are easy to calculate. Let's first look at the total passwords. This is an example of a list with repetition. There are 26 lowercase letters, 26 uppercase letters, and 10 digits, for a total of 62 different characters. Each word is made up of 8 different characters, and so the number of total passwords is 62 to the 8th power, because each position has 62 choices. What about the passwords with no repeating characters? This is an example of a list without repetition, and we learned in the last video that this is an example of a k permutation, where k is equal to 8 and n is equal to 62. And so the number of passwords with no repeating characters is p of 62, 8. We'll copy these two expressions above, and that tells us that the answer to the question is 62 to the 8th minus p of 62, 8. Just leave your answer in this form. It's much more descriptive than an explicit number. Let's do another example. This picture should look familiar. The question is, how many binary words of length 10 have at least 2 ones? We drew this picture before. The set of all binary words can be broken down into words that have 0 ones, 1 one, 2 ones, 3 ones, etc. up to 10 ones. The universe is the set of all binary words of length 10. How many of those are there? There are 2 choices for each character, and there's 10 characters needed. So there are 2 to the 10 binary words of length 10, and now we're going to apply counting the complement. We want to count the number of words in this part of the diagram. That's the good set. It's the set of binary words of length 10 with at least 2 ones. Let's ask ourselves, what is the complement of this good set? In this case, the bad set is the set of binary words of length 10 with less than 2 ones, which we can break down into those with 0 ones and those with 1 one. Which words have 0 ones? They have to have all zeros. So there's exactly 1 of these. How many binary words have 1 1? 1 0 0 0 0 0 0 1 0 0 0 0 0. In fact, you can place the 1 in any of the 10 positions. So there are 10 different binary words of length 10 with exactly 1 1. That tells us that the number of elements in this bad set is 11, and therefore the answer to the question is 2 to the 10th minus 11. In these two examples, it was easier to count the whole set and the complement of the set that we cared about than it was to count the set that we cared about. And that's why counting the complement was helpful here. This counting question was of a type that you'll see over and over again. It's a question that involves restrictions on types of objects. Both of the questions that we saw were of the form, how many somethings are there such that something is true? We've seen that here with counting the complement, And we'll see this in the next two videos as well. So how do we approach this type of question? First, we try to understand the universe, and then we use the restrictions in the question to define the sets in the universe. In the previous example, we were talking about binary words with a restriction that it has at least two ones. And that was our rule to define the set that we cared about. Then we need to ask ourselves the question, can you count these sets directly? If so, go ahead, do it. You don't need to use a technique like counting the complement. If, on the other hand, after you find the sets defined by the restrictions, your question involves one set that is difficult to count directly, you should try counting the complement. You'll see if the complement is easy to count, and if so, you're all set. The last situation is that your question involves multiple sets instead of just one set, and often those sets will overlap or interact in some way. When you're in that situation, you'll want to use Venn diagrams and/or the principle of inclusion-exclusion, which is the topic of the next few videos, to understand how the sets and the universe interact. All right, let's head over there. See you soon.